spent the last couple of days talking about kinetic energy and potential energy, and we had a couple worksheets for homework last night. Kinetic energy worksheet number 1 and worksheet number 2, potential energy. We got one request to go over one of those questions that we had for homework last night. That's question number 10 on the first worksheet. It says, what's the speed of a 20 Newton object that has a kinetic energy of 9.00 joules? Remember that kinetic energy is the energy of motion. Anything that's moving has kinetic energy. And if something has stored energy, energy that's not doing anything right now but has the potential to cause something to move, then it's got some kind of potential energy. Clearly, this is a kinetic energy question, a 1/2 mv squared question. But what do we got for givens here? Well, we know the kinetic energy, EK, is 9.00 joules. What's this whole 20 Newton thing? Sounds like a force, right? Not a mass. We want a mass. This sounds like a force. Specifically, what force is it if it's 20 newtons? It would be the force of gravity. It's the weight of the object. We're looking for the speed of the object. Well, from the weight of the object, we can find the mass. We know that weight, or force of gravity, is equal to m times g. So we'll just rearrange that to solve for mass. It's the weight, or the force of gravity, over 9.81. 20.0 newtons divided by 9.81 meters per second squared. Who's got an answer for that mass there? 2.0388, thank you. All right, that's the mass we want. Now, all we're going to do is plug it into my kinetic energy equation, 1/2 mv squared. And don't forget to square v. Oh, sorry, we're going to solve for v, aren't we? So let's actually rearrange this equation first here. Let's take the 1/2 m down by dividing. I get EK over 1/2 m equals v squared. And then, of course, I've got to square root both sides in order to get v by itself. So it's going to be v is equal to the square root of EK over 1/2 of m. So it's the square root of 9 joules over 1/2 of 2.0388. Let's do this one on the calculator just because it looks a little bit ugly. Do it together here. Let's say 9, that's my kinetic energy, divided by, let's see some brackets here on the bottom, 0.5, that's a half, times 2.0388. Okay, that gives me what's inside the square root sign. But you got to remember, I should say, to square root that number. So when I do square root 8.828, I end up getting 2.97 meters per second. How many people actually got 2.97? The dyslexic part of me there acting up. 2.97 meters per second there. Good. Right? How many, just out of curiosity, how many people forgot to square root that, at least first, until they saw an answer? Nobody? Oh, you're lying. You're lying. Somebody forgot to square root that. Okay. Two common mistakes with this equation are when you're calculating kinetic energy, forgetting to square v, and when you're calculating v, forgetting to square root the other side. Yeah, I've seen that a million times. Hopefully I don't see it again with you guys. All right, we're good there? All right, I want to move forward a little bit here today. Still talking about energy, still talking about forces. Just the two together a little bit more than we have in the last couple of days when we were talking about kinetic energy and potential energy. No, I want to talk about work today. We're going to define work as the change in energy experienced by something. Nick, how much energy does your desk have right now? 0. It's on the ground, or at least relative to the ground. You could say relative to the center of the Earth, it would have a potential energy, right? But relative to the ground, it has 0 potential energy, and clearly it's not moving. So we'd say that it has 0 kinetic energy as well. We'd say that its total mechanical energy, by the way, is the sum of potential and kinetic energy. Its total mechanical energy is 0. Well, if we want to change the energy of Nick's desk, then we have to do work on Nick's desk. How do we do that? Like, seriously, like, let's take a step back from this for a second and think logically. How do we do work on Nick's desk? Thinking about what work means. Work is a change in energy. How do we change the energy of Nick's desk? Right now it has 0. How do we give it something? What do we got to do to it? Yep, what's one thing? You got to move it. Okay, so there needs to be movement. Okay, if it remains at rest, there's no way that there's going to be any work done on it. We need movement. How do we get movement, David? You got to apply a force to it, right? So you got to push it or pull it, and you got to move it as you push it or pull it. It's not good enough just to push his desk. We know that a force can do two things. It can accelerate an object, but it can also deform an object. If I apply a force to deform an object, then it doesn't mean it's any easier on me, but I certainly haven't done any work on his desk because I haven't changed the energy of his desk. But if I apply a force and there's movement as well, then his desk gained a little bit of kinetic energy in that process, right? A change in energy is work. So the two things that are required for work to be done, we got to apply a force on the object, and we also have to move the object. Now, the force and the displacement have to be parallel to each other. In other words, they have to be in the same direction. In other words, if Nick's desk, for whatever reason, just happened to be sliding across the floor, because maybe somebody else gave it a big shove, and I push on his desk downward, and it's still moving horizontally, it's got movement, and it's got a force applied to it, but my force hasn't caused the movement. So I still haven't changed the energy of his desk. Let's think about that, right? Something's sliding horizontally. I push on it downwards. That's not changing the energy of the object. In order for me to do work on the object, I must push on the object in the same direction or opposite to the direction of the displacement. If they're not parallel to each other, the force and the displacement, that is, as is in the case of, say, a wagon, right? We've used that wagon example quite a few times now. You pull with a force like this of 100 newtons, but the wagon moves horizontally this way. They're not parallel to each other, right? What we'd have to do in that case is find a component of the applied force that is parallel to the direction of movement. Just out of curiosity here, let's say that angle is 30 degrees, because that's always what we make the angle. The x component of that force, that applied force, is what moves it parallel to the direction of movement. How would we find that x component? Which trig function would we use to find that x component? That would be, go ahead. It would be cosine, right? So we could say the x component of that force would be cosine theta is equal to adjacent over hypotenuse. So we would say, in other words, that the x component was f cosine 30 degrees. You got a funny angle, you'd have to get rid of it. But the good news is there's an equation that already has that done for us, that deals with the component of the force that's parallel to the direction of the displacement already. We know that work is equal to F times D. By the way, force is a vector, displacement is a vector, but when we multiply a vector by a vector, we end up getting a scalar. Work is a scalar. Now this assumes that the force is parallel to the displacement. If it's not parallel to the displacement, we would have to replace this with F cosine 30 degrees. So what we end up seeing is a slightly modified version of this equation. Looks like this. W is equal to F cosine 30 times displacement, or we could say F times D times cosine 30 degrees. Sorry, cosine theta, I should say. This is the equation that you're going to see on your data sheet. W is equal to FD cos theta. If the direction of the force and the movement are parallel to each other, then the angle is going to be 0. If the angle is 0, Hit on your calculator right now. Right now, cos 0. What does it equal? Some of you may just know that already without doing it on your calculator. What's cos 0? 1. Cos 0 is 1. So if the object is being pushed or pulled in the same direction as the movement, same direction as the displacement, theta is 0, and cos theta is 1. So you just end up dropping the cos theta, right? It becomes F times D. If you push it to the right and it moves to the right, then the equation is FD times cosine 0, or in other words, it's just FD. But if you pull it at 30 degrees and it moves to the right, then we have to include that theta, the angle between the way that it's pulled and the way that it actually moves. Got it? I'll tell you, probably about 8 or 9 times out of 10, you can end up dropping the cos theta. You can end up just ignoring the cos theta. Why? Because you end up pushing it in the same direction as it moves, and theta ends up being 0, so cos theta ends up being 1, and it just disappears from the equation. But then there's that 1 time out of 10, or 2 times out of 10, where you are pulling or pushing at an angle relative to the way that it moves, and you've got to include that. All right? Okay, before we do an example, I just want to show you a couple different scenarios here. Here's the wagon again. Moves to the right. Would I use F times D for this, or would I use F times D times cos theta for this one? First part of the equation, or do I use the whole thing, F times D times cos theta? It's the whole thing, right? What's the value of theta in this case? This is not a trick question. What's the value of theta? 30 degrees. So whatever the force is times however far the object moved times cosine of the 30 degrees. What about this one? Let's say it's moving this way, and I apply a force this way. What's the angle now? Yep. 0. So I can drop that, right? I can just make it F times D if I want. How about this one? It's moving this way. It's got inertia. It's moving this way. But yet I apply a force this way to slow it down. What's the angle now? Technically not 0. Technically it's 180. Hit cos 180 on your calculator. What does it equal? Natalie, what's cos 180 equal? Negative 1. So in other words, the cos theta still disappears. It just becomes a negative value of work, which means it's an energy lost, right? Work is a change in energy. If you get a negative value for work, it's energy lost. And that should make sense. If it's moving to the right and you apply a force to the left, you're taking kinetic energy away from the system. It's an energy lost. But in the end, you can still make it F times D. You don't have to worry about the cos theta on there. Oh, what about this one? This one's a tricky one. What's theta in this case? What's theta right here? Rosie? 0? Who says 0? Okay, 3 or 4 of you. Doesn't look like it's 0 to me. What is it, Donna? Oh, you're agreeing? Okay. Anybody say something different? If I say 30 degrees, who says it's 30 degrees? The angle is 30. Nobody. All right, good. You're right, Rosie. It is 0 degrees. Why is the angle 0 degrees here? Go ahead. Yeah, that's exactly right. Theta does not stand for any angle, just any random angle. Theta stands for the angle between the way that we move, we push it or pull it, and the way that it moves. Hey, I'm pulling it parallel to the hill. It moves parallel to the hill. It doesn't matter what the angle of the hill is. Okay, that's irrelevant for purposes of work. We're pulling it in the same direction as it moves. Theta ends up being equal to 0. Guys, most times we're dealing with a situation like this, right? Where it's being pushed or pulled parallel to the way that it moves. Okay, So theta would either be 0 or 180, which means that we could drop the cos theta and most times just leave the equation this way, F times D. All right? Let's have a look at an example 6.1 on page 294. It says figure 6.8 shows a force of 150 newtons at 0 degrees acting on an object that moves at 25 degrees while the force acts. What's the work done by the force? What's my angle here? Is it 25 degrees or is it 0 degrees? It's 25, right? I'm pushing it one way and it moves a different way. So that means that only a component of the force actually goes into moving it. Some of the force is wasted, right? Only part, the x component of the force is causing displacement there. So what I'm going to do is say W is equal to F times D times cos theta. If theta was 0 or if theta was 180, I could just drop that, but I can't here. I'm going to sub in the value of F, 150, times the displacement of 25.0 meters, times cosine 25.0 degrees. Not a hard question, as long as you recognize when to use that angle and when not to use that angle. Let's say 150 times 25 times cosine 25 degrees. We end up getting a value of 3398.7. The units are joules because work is a change in energy. Rounded to 3 digits, 3.40 times 10 to the 3 joules. So what does that really mean? We just calculated the work done by the force, but it means that's the energy that this object gained, the energy that it gained as it was moved through that displacement of 25 meters. Let's have a look at questions 294. Oh, sorry, questions on page 294, questions 1 to 4. See what you can do with those at your desk now. Simple. Want to do one more example before we wrap it up for the week. If there's a 20 kilogram object gains 300 joules of kinetic energy as it's pushed a distance of 100 meters, calculate the force used to push the object. Hey, what are we really given here? A gain of energy is defined as what? Work. An object gains 300 joules of kinetic energy. That's the work done on the object, right? The mass is 20 kilograms. Our displacement is 100 meters. We want to find the force. Doesn't look like the mass is even relevant here, right? We're going to say W is equal to F times D. Let's assume that it moves it in the same direction as the force is applied. Doesn't actually say that, but we don't have any indication of an angle, so I think we have to assume that. Rearrange this to solve for force. Becomes W over D. So it becomes 300 joules over 100 meters equals 3.0 newtons. Here's a follow-up question for you. If it starts at rest, what's its final speed? If it starts at rest, what's the final speed? Well, there's a couple ways that we could go about doing this, but my suggestion would be to say, hey, we know that work is equal to F times D, but we know that work is equal to the change in energy as well. That's the definition of work. It's the change in energy. The final energy is, what kind does it have? This thing is moving, right? So it's got kinetic energy at the end of it. What kind of energy did it have at the beginning when it began at rest? Nothing. So why don't we say delta E of 300 joules, or a work of 300 joules, is equal to 1/2 of 20 kilograms times VF squared. All we're doing here is setting, in the first part of the question, W equal to F times D. All we're doing in the second part of the question is recognizing that work is the change in energy and looking at what kind of energy changes there. 300 divided by 1/2 is 600. 600 divided by 20 is 30. And we're going to take the square root of 30, which is, VF ends up being equal to 5.48 meters per second. So what's the force? Well, I'll recognize that work is equal to the change in energy and sub in 300 joules for work. And then what's the final speed? You could do an F equals MA calculation, okay, solve for the acceleration and so on. But I think it's just as easy to do it this way, to say W is equal to delta E, or 300 joules is equal to the final kinetic minus 0, the initial energy. Solve for it that way. All right. I would like you for homework this weekend to work on the first worksheet that's getting handed out now. It says worksheet number 3, work. And I'd like you to do that whole worksheet, all 5 questions. Worksheet number 3, questions 1 to 5. The first 3 questions are rather straightforward like this. The last 2 questions are a little bit more like this. So keep that in mind as you're working on these questions, right? The first 3 questions, you know, W is equal to F times D. If you have an angle, deal with it, right? Make it FD times cosine theta. If you don't, then just drop the cos theta. But if you're looking for a final speed, or you've got an initial speed or so on, you're probably going to use this thing, right? Delta E equals 1/2 mv squared minus 0, or 0 minus 1/2 mv squared, whatever's happening there. All right, last couple minutes, you can work on that worksheet as well.